Welcome back, everybody. This is our third video on numerical integration. In this video, we're going to explore what's called the trapezoidal rule, and then we're going to do an example that shows how the left endpoint, right endpoint, midpoint, and trapezoidal rules all work in practice, and compare how numerical integration, video 3, take 3. Hi everybody, welcome back. This is our third video on numerical integration. Take 4. Welcome back everybody. This is our third video on numerical integration. In this video we're going to first start with the trapezoidal rule. Then we're going to move into an example where we show the left endpoint, right endpoint, midpoint, and trapezoidal rules in action and see how accurate they are versus one another. Alright, so let's start with the trapezoidal rule. So the trapezoidal rule, as the name suggests, is about approximating the area under your curve, not with rectangles, but with trapezoids. So let's give it a try. So say I wanted to find the area under this curve just as before. I break it up into these same intervals, and now I look between x0 and x1. I could sample the function at x0, like with the left endpoint rule. I get a y0. I could sample the function at x1, and that would give me a y1, just like I was doing in the right endpoint rule. The midpoint rule would say, well, use the point that's sort of in the middle here, and then find the value of the function at that point. The trapezoidal rule instead says, take the average not of the inputs, but of the outputs. Right? Find the number that's in the middle. How does that show up? Well, we'll see that in a second. I said there's going to be trapezoids, though. So why don't we connect these two dots with a straight line? That gives me a trapezoid. I get a nice trapezoid here. I can fill it in. I get a nice area. And you can see, unlike when I had the rectangle that had height y0, which was way too small, or the rectangle which had height y1, which was way too big, this trapezoid looks pretty good. Right? How do I find, though, the area of this trapezoid? Because, well, what's the next thing I want to do? I want to write down here, area is approximately equal to, I don't have rectangles anymore, I need the area formula for a trapezoid. But that's the good news here. Area formula for a trapezoid, very simple. You take the base, okay, that's going to be delta x all the time, times, well, it's not the height of the trapezoid. The trapezoid doesn't have a height, but you might call it the average height of the trapezoid. So the height on the left is y0, the height on the right is y1. The average height, well, it's just the average of y0 and y1. The way you compute the average of two numbers is you add them together and you divide by 2. So this is how I'm going to find the area of this trapezoid. Fine. I do it again. I go to the next interval. I go from x1 to x2. I sample at x1. Well, I already got that. There's my y1. I sample at x2. Okay, there's my y2. And now I connect these dots, and I get a nice trapezoid. Again, the area of this trapezoid is going to be base times the average height. So what's the average height of this function? Well, the average height, again, is just the average of y1 and y2. So plus y1 plus y2 over 2. Okay, I think there's one more to do here. So we go x2 to x3. I sample at x2. Hey, we've already done that. That's y2. I sample at x3. Okay, there's my y3. I now connect with a straight line. And now I get this nice trapezoid. Again, the area is going to be the base, delta x, times the height. Right? But what do we mean by the height? We mean the average height, which is going to be y2 plus y3 over 2. Okay. So I get this nice formula for the trapezoid. All right, we're going to clean this up a little bit, and I'll show you maybe a slightly different variation of this formula and then we'll come back and do a great example. All right, so we take a look at this formula here, and we've already factored out the delta x, right? We did that right from the start, but you'll notice there's a 2 in each of these fractions. We could pull that out as well. Yeah, let's give it a try. If I factor out that 2, then I always have half of delta x, fine. And what's going to be left? Well, it's not hard to write it down, but let's talk about it. So you have the y0. Okay, we can get that. But then you notice the y1 appears twice because we used it as both a left endpoint of some trapezoid and as a right endpoint of some trapezoid. So I'm actually going to get 2 copies of y1. And similarly, y2 appears twice. In fact, all of these points on the interior are going to occur twice, once as a left and once as a right endpoint of a trapezoid. So all the ones in the middle will get a coefficient of 2. And then I'm left with, finally, the right endpoint. Okay, so I have the x3 term, which gives me the y3. So that's only going to appear once because it only showed up on that final trapezoid. Okay, so we have a slightly simpler version of this formula for the area. So whenever you're trying to use the trapezoidal rule, you'll divide up your interval into subintervals. The length of those intervals divided by 2, that you're going to pull out. And then all you have to do is sample the function at each of these points, x0, x1, x2, x3, or however many you have. And anything in the middle, right, anything that wasn't an original endpoint, is actually going to get an extra coefficient of 2 each time. Okay, a little strange that this happens. Okay, but we'll see this actually show up in a later video when we do Simpson's rule. We'll have even stranger coefficients. But this is a typical thing that can happen. All right, we're going to clean this up, and we're going to do our nice example. All right, so here's the long promised example. We're going to look at f of x equals negative x squared plus 4. I chose this not because it's inherently difficult, at least not to us. We know how to compute this just using a straight integral. But that's going to actually give us the exact answer, allowing us to compare all of these approximations and see, okay, which one is really doing the best. All right, so in order to do all these approximations, we're going to need a bunch of data. Let's just do it all at once if we can. So I'm going to need, for some x values, some f of x values, right? These are our y's. All right, now let's see, what are we going to need? Well, first, I need to specify my domain of integration. So I'm really asking you just between 1 and 2. So I want to know what's the integral from 1 to 2 of negative x squared plus 4. All right, and again, we can just use an antiderivative to get the answer, but let's do this numerically. I'm going to chop this up. I'm going to do this very, very simple. I'm going to chop it up just into 2 intervals. Okay, so I'll chop right down the middle. So there is 1.5. All right, and so those are going to be the 2 intervals. So my delta x is just going to be a half, 0.5, because that's the length of that interval, 1 to 1.5. All right, so we know for the left endpoint approximation, we're going to need the 1 and the 1.5. For the right endpoint approximation, we'll need the 1.5 and the 2. For the midpoint, we're going to need 1.25 and 1.75. Okay, let's toss those in the middle here, because those were our midpoints of the intervals, 1.75. So in total, we're going to need to sample f at 5 points to get all of these different approximations. So let's see. So we're going to need x at 1, 1.25, 1.5, 1.75, and 2. All right. So no sense in going through all these computations, just plugging numbers into this formula. But when you plug 1 in, you get out 3. If you plug in 1.25, you get something very nasty, 2.4375. If you plug in 1.5, you get 1.75. If you plug in 1.75, you get 0.9375. And if you plug in 2, well, that's actually the easy one, you get 0. All right, so we're going to use all this data now to write down the different approximations. So let's start with, we'll abbreviate here, the left endpoint approximation. So this is going to equal, so let's see, we need our delta x, that's 0.5, times, and now what are we going to do? We're going to add up the y value, the f of x, at the left endpoints, okay, so that we don't include the 2. So we need a 1 and 1.5. So we get a 3 and a 1.75. That's not so bad to do, right? Okay, so you could work this out if you needed to. Let's see, I worked it out and I ended up with 2.375. Okay, so that would be the approximation of the area under this curve between 1 and 2. Okay, how about a right endpoint approximation? To use the right endpoint approximation, again, I need my delta x, still 0.5. And then I need to use the right endpoints, so 1.5 and 2. So I need to find out their f of x values here. So at 1.5, the output was 1.75. And at 2, oh, that's nice, it's 0. Okay, so we add that together and we end up with 0.875. Now let's stop. There's a pretty big difference here. 2.375, 0.875. Those aren't really all that close. All right. We maybe get a sense that this one is probably a little too big and this one's probably a little too small. Okay, so maybe the correct answer is somewhere in the middle. Let's see. Let's try the midpoint rule. So the midpoint rule, what do we need? We need the base, or the delta x, that's always 0.5 still. And then we need to evaluate not at the left or the right endpoints, but at the midpoints. So 1.25 and 1.75. So at 1.25, we end up with 2.4375. And at 1.75, we get 0.9375. And if we tabulate, this ends up being 1.6875. Hey, somewhere nicely in between 2.375 and 0.875. Okay, that gives us some hope that we might be getting closer. Okay, and finally the trapezoidal rule. So with that, again, we need the base, which is 0.5. And then what is it we needed? We needed the average of the y values at these endpoints. So we need the average of 3 and 1.75, and then the average of 1.75 and 0. So we compute 3 plus 1.75 over 2, and 1.75 plus 0 over 2. Or we could have used that slightly simpler formula. We take 0.5, divide it by 2, and then we just write down, okay, first the first y value, which is 3, and then 2 times the middle y value is 1.75, and then the last y value only gets a coefficient of 1, which is a 0. Okay, so what does that end up being? Well, this ends up equaling, we'll put it on this side because we've run out of space, that ended up equaling 1.625. Okay, so in total we have 4 different approximations. 2.375, 0.875, 1.6875, and 1.625. Which of them is best? Well, we can actually compute this. Let's see. This is negative x cubed over 3 plus 4x, evaluated between 1 and 2. And I'll jump ahead and let you know that this ends up equaling 1.6 repeated. All right, 1.6666, etc. So which one was closest? Well, let's see. The left endpoint, yeah, that's pretty far away, all right? 0.7 or so. Okay, the right endpoint, yeah, also 0.8, 0.7, right? How about that midpoint rule? Ooh, that's not too bad, right? 1.6, it matches, only off by 200ths or so. And the trapezoidal rule, 1.625, about 400ths or so. So in this case, midpoint rule is the winner. Do you have a suspicion as to which one is usually going to be the winner? So if you draw enough pictures, you might be able to convince yourself that the trapezoidal rule should be the winner. It turns out it's usually not. In fact, the midpoint rule is usually about twice as accurate. That is, the error of the midpoint rule will be about half as much as the error for the trapezoidal rule. But they both kick left and right endpoints butts, okay, in a contest. Okay, so In practice, the midpoint rule, that seems like the one you'd want to use. Again, though, it may depend on what kind of data you have. We're going to see in the next video, though, an even better rule. See, what we've done so far is approximate everything with essentially lines. They were either horizontal or maybe they were sloped, but they were always lines. And if you look at something like this, you say, well, that looks kind of like a parabola, well, because it is a parabola. But even in the previous video examples, you had some real wavy stuff, but if you just looked locally, you said that's very parabolic looking. Why don't we approximate with parabolas? And that's going to be the subject of the video on Simpson's rule.